This video follows from the two-sample pooled hypothesis test. We're going to use the same problem statement to do the 99% confidence interval. And since it's a confidence interval, we're going to need the critical number for t at 99%. So let's find that right now. Let's go over to the t-table. Here's 99%. And we have 60 degrees of freedom, recall from our previous video. So we're going to use 2.660. I'm only going to use the 3 decimals in this computation. Okay, there's that. Now, the two-sample pooled confidence interval, and recall that pooling is determined, unless you're told otherwise, by the big standard deviation divided by the small. And this ratio is less than 2. This is why we would use pooling here. Now, let's get the formula on the screen, and then we'll plug some numbers in. So we want the difference. So let's go with y bar 2 minus y bar 1. And this is my own personal style. I like to avoid negative numbers. Now we have a critical number. Now we need the pooled term, which will be n sub 2 minus 1 times s sub 2 squared. And then we're going to repeat that with the other sample, n sub 1 minus 1 times s sub 1 squared. And n2 plus n1 minus 2. And this is where we're getting our degrees of freedom from, by the way, as well. And then we also have another square root, which is simply 1 over n2 plus 1 over n1. Now, pro tip, we've already computed this. We did that on the hypothesis test earlier, and it had a value of 1.04. I'm not going to plug the numbers in to recompute that, since I don't have to. Which isn't to say that perhaps if you're just looking at this video by itself, this is what we computed earlier. Go back and take a look at the two-sample pooled hypothesis test, and you'll see how we got the 1.04. However, let's carry on. So this is going to be 24 minus 22, plus and minus, our critical number, 2.660, times 1.04. So this will be the margin of error, and we need to multiply that out. So let's grab a calculator and do that. And see what we actually get here. So we have 1.04 times 2.66. And our margin of error then is 2.766. And we'll add and subtract that from the difference in mean values. Okay, let's go over here. Our estimate of the difference is 2. And if I subtract 2.766, I'm going to have negative 0.766. That's my lower bound. If I add the two together, I get 4.766. Now, you'll notice that 0 is in the interval. And when that happens, this is a fail to reject the null hypothesis conclusion in context of a hypothesis test. Let me finish writing this word out here. The other thing we can say about this, if we wanted to talk about it specifically in context of confidence intervals, we can say that with 99% confidence, we believe the true value of the difference between the two means lies between negative 0.766 and positive 4.766. And again, the conclusion remains the same, since the hypothesized difference of 0 from the null hypothesis is also in that interval. We cannot say that it is unlikely to be true, which is why we would fail to reject the null hypothesis in this context. Fail to reject. There we go. Boom. Done. Now, the problem is much easier, if you recall what I said earlier in our video, if you save the numbers from the hypothesis test. Save yourself a lot of time. It's quite a bit of a tedious computation with the calculator. Anyway, if you didn't save it, that's not the end of the world. Just take your time and separately compute each square root term and then multiply them together just to minimize the chance of error. But there it is, the pooled two-sample confidence interval. And that ends this video.